Nice. Oh, no worries. Take your time. You're good. Thank you. Yep. Hey Josh, how's it going?
Good.
You have a good birthday Monday?
I did have a good birthday. Yeah, it was nice. I'm very scared of being 13 at this point though, because I have that like sinking suspicion all four classes, like, the stars are aligning to hurt me. All four will hit me with an exam that week.
It kind of ends up like that a lot of the time.
Yeah, so that's scary. Other than that, I'm fine. That week, though, like, I'll be seeing things that don't exist. Like, reality is no longer important or feasible. Um, but that's a future Josh problem. Yeah, because at least like last time, the class that has take-home exams was on a different week, so I could just dedicate a bunch of time to that. It's like,
Yeah.
oh gosh, I don't want to have that looming over while I have like normal exams.
Mhm.
But the week's been pretty good. I did SI and witch trials in my SI session for like Halloween because it's
Yeah.
a session.
Yeah.
That's also why I'm dressed like this.
Uh-huh.
It was pretty fun. I can show you if you're curious. I did have one question too, because I got a weird result for some of the math labs.
Sure. Uh-huh.
Mostly I'm doing pretty well on the homework, but that one where it's probably just a typo somewhere, but I wanted to see. I might have done something. Oh. Here. So I plotted, like the position, this matches just about exactly what you'd had for like the position as a function of time. And then this one though, I'm getting like the 0.8 newtons. Did I do something like foolish? But I converted like the radians into degrees. Was that a mistake?
If you're using the degree version of the sines and cosines, that's
Because
fine.
I did, sine b here.
Yeah,
But I converted, this was in radians per second, and then I converted it to degrees per second.
Yeah, that's fine.
Okay.
Yeah, that's fine.
Huh.
So what graph was that again?
That was for force, because I called it force y equals mass times the theta dot squared times the sine b of theta. Did I forget something?
Are you missing gravity there?
Am I missing? Is that off?
Because if it's off by about a factor of 10.
So if I just do times 9, that makes a lot. Man. But wouldn't the acceleration just be the acceleration? Oh, is it just because that was the acceleration just as time and then gravity's like the constant one on top of that?
No, so I mean you're doing a force balance, right? And so the force, you're solving for the force, the centripetal force, right? And so everything there needs to have units of force. And so you can't just do mass. Well, you have mass
Because
times.
this should have been the acceleration because the theta double dot.
Oh, there's a constant gravity force there as well.
That's what's off.
So you have to I think either add or subtract it at 9.8 times mass.
Okay, that makes sense. Then it's looking, I think, pretty good.
Yeah.
Hey.
Yeah.
On Monday, will there also be like a graph project info?
Yes.
Okay.
Yeah. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. All right, so today the plan is we're hopefully going to finish up our lecture notes on human motion kinematics. So we're going to be talking about transformation matrices today. So a lot of vector algebra today. So I hope you guys are prepared for that. One announcement that one important announcement that I do want to make is we're very kind of quickly approaching kind of the end of the semester. So it's just about time for us to talk about the final project in the class. So Monday, I'm going to have the formal instructions for everybody. So I'll have the specifications ready. We'll go over them together in class to kind of discuss what the requirements are and what the expectations are. Okay. So just to kind of give you just a very brief nutshell, the final project in this class, it's a group project. And it's basically kind of like a group research project. So, everything that we've been going over in the class so far has been, kind of just general biomechanics. But in reality, you can apply a lot of what we're learning in this class to lots of different areas out there. And so, for instance, you can apply what we learned to, to really study proper workout technique. And so I had a group that did that last year. Had a group that, actually used what we learned in the class to explore, animal motion biomechanics as well. So how lions and cheetahs and stuff, how they move, how their gait is, and how that differs from humans and how that's advantageous for, for wild animals too, right? So basically the idea with the final project is to choose a specialized topic, do research on it. So, actually look into primary literature, look into, scientific articles, take what we learn in the class, all the techniques that we've learned for biomechanical analysis, and then apply that to your specific subject, right? And there's two main deliverables. So there's going to be a final presentation that your group will give in the final week of class. And then there's a final report that's going to be due after finals week. Okay. All right, but I'll have more specifics for that for you on Monday. So definitely, make sure you come on Monday, or at least tune in on Monday to get that information. And at the very least, you should start thinking about the groups that you're going to form as well. So Groups for this class will be, we're just at right about 29 students for the class. And so the group sizes will be about 4 students each. Okay. We may have a couple groups with 3 students, but we should match up pretty well with 4 students. So if you have friends in the class, definitely reach out to them, see who's willing to make a group together, and then start thinking about the topic for your final project. Okay. All right. Any questions on that, or just any questions on anything else before we get started? Okay. All right. So let's go ahead and pick up where we left off. Okay. So on Monday, we were talking about this idea of using optical motion capture to capture kinematics. Okay. And kind of the setup that we were going with was something like this. All right. So, the human body consists of all these different rigid segments of the body. And we want to find out, how these segments are moving relative to one another. All right. And so our goal when we're capturing human motion kinematics, I've already used red, I'm going to use green. Okay. Is to capture this information right here. Okay. Right? So between every segment of your body, there's a joint of some kind, right? So we've gone over joints before, like your elbow joint, your shoulder joint, right? The orientation of the 2 body parts that articulate at the joint can be described by the joint angles. And so our objective, our goal in tracking human motion kinematics is to find out or have a way to compute and track these joint angles as a function of time as the person goes through their motion. Okay. And so the way that we're going to do that is, we're going to attach a coordinate system or a reference frame to every single segment of the body. So everything that can kind of be considered one, that moves as one. And we want to find out, how these reference frames, what their orientations are relative to one another as the person goes through the motion. Okay. So that's our objective. And so to facilitate this analysis, we need to have some kind of mathematical tool that can help us transform from one coordinate system to the other, right? And by forming that transformation, we'll be able to find out what these joint angles are, right? And so that mathematical tool is going to be the subject for today's lecture, which is called transformation matrices. Okay. All right, so the objective here is to have some kind of, and what these transformation matrices allow us to do is that they give us a way to quantify the relative orientation of one reference frame compared to another. Okay. That's not the only thing that they do. And so transformation matrices are actually used for a lot of other things, but that's one very convenient way that we can use them. Okay. Okay. So the idea is that, if you have a reference frame, we'll call it X and Y. Okay. So this reference frame may be attached to, one of the segments of your arm. So let's say your upper arm. Okay. And if we have a different reference frame, so let's say this is the reference frame of a body segment that's neighboring the upper arm. So let's say it's the lower arm. Okay. Maybe that reference frame looks something like this. All right. Or that rotation angle there is theta. Okay. So to go from reference frame 1 to reference frame 2, you can see that we do a simple counterclockwise rotation by an amount theta. Okay. And so the transformation matrix is going to embed that rotation angle into it. Okay. But what is a transformation matrix in general, right? So the idea with the transformation matrix is actually to basically reform our coordinates, right? So if we have a point P, okay, so let's say we define a point P in our original reference frame there, okay? If I take that same point P and put it in the other reference frame, how we describe the location of P depends on our reference frame, okay? So, I try to draw it so that they look the same, but this P physically is in the exact same location, okay, in both frames. Okay. It may not look like it because I'm terrible at relative drawing, but imagine that they're in the same location, right? But what's going to be different between the two frames is how we describe where that location is, right? So how do we usually describe location in a Cartesian axis? Well, we usually give it its x and y locations, right? So we say this is located at px, comma py, right? So that's kind of the most usual way. We have the coordinates of the point. But what is px and py, right? One way that we can think of px and py is that those are the distances between the point P and the neighboring coordinate axes, right? And so this distance right here from P to the x-axis, we know this is py, okay? And the distance from the y-axis to the point P, this is px, right? So what we understand is kind of the coordinate locations of a point is nothing more than just the distance from that point to the axis, okay? We can describe the same point P relative to a different coordinate system, right? So if you rotate the coordinate system up, this is going to have a new coordinates, px prime and py prime, okay? Where py prime is the distance between P and the x prime axis, and px prime is the distance between the y prime axis and the point P. Okay. All right, so P may be in the exact same location, but how we describe that location depends on our depends on the orientation of our coordinate system. Okay. It's like, when you're describing the location of something to someone, right? So usually you say like, oh, turn right at the Target, or turn left at the McDonald's or something like that, right? So everything is defined kind of relative to either to some landmarks. Okay. Okay. So even though P is in the same location, in both reference frames, generally the coordinates are going to be different in each of the reference frames, right? So Px and Px prime are different. Py and Py prime are different from each other. Okay? All right. But if we know what the transformation was, and so if we know the mathematical kind of, or I would say physical kind of operation that took us from one reference frame to another, we can use that information to transform from the coordinates in one system to the coordinates in another system. And that is exactly the purpose of the transformation matrix. Okay. Okay. So how do we get this transformation matrix? Or I guess, let me pause here for a second. Are there any questions on this so far? Okay. Okay, so how do we get that transformation matrix? Well, the idea of the transformation matrix is to go from one coordinate set of coordinates to another, right? And so it can look something like this. Right? So let's say that we have, the coordinates in the prime coordinates. We have px prime, py prime. Okay, I'm putting it in a column vector just to kind of make things convenient for calculation. Okay. And so my argument here is that if we take the coordinates in the original reference frame, px and py, okay, if we multiply those original coordinates by some matrix here, okay, so this is going to be our matrix T, which is our transformation matrix. Okay. Then we can transform those coordinates from one system to the next. Okay. So this is kind of generally how we do this, just because with this transformation matrix, performing a transformation is just a simple algebraic operation. So you take the original coordinates, you multiply by the matrix, and then you get your coordinates in the new system. Okay. All right, so how do we obtain this matrix? Well, what do we know about a matrix set of equations? We know that matrix set of equations are nothing more than just a linear system, right? And so let me go ahead and just kind of redraw this, right? And so first of all, we can kind of, guess the size of this matrix as well. And so we're multiplying this matrix by a 2x1 matrix. So that means the number of columns in the matrix has to be 2. And then we're getting a 2x1 matrix in here as well. So that tells us our transformation has to be 2x2, at least in 2 dimensions. Okay. And so we're going to have T11, T12, T21, and T22. Okay. Right. And so by simple algebra, what we can see, we can actually write out the 2 equations by actually multiplying the matrix by the vector, right? So our 2 equations here, if we multiply the first row of the matrix, is we get px prime is equal to p11 multiplied by px plus t12 multiplied by py. And our second equation, py prime is equal to t21 px plus t22 py. Okay. All right, so these equations tell us that, each coordinate in the rotated reference frame here can be obtained by a linear combination of the coordinates in the original reference frame. Okay. And so the question is, how do we obtain these transformation constants here? Okay. So how do we obtain T11, T12, T21, and T22? Okay. Okay. So to obtain those, let's use a little bit of geometry. Okay. So let me go ahead and draw our 2 reference frames here one more time. Okay. So for this first section of the class, we're just considering a simple rotation, and we're in 2D, right? So we'll generalize these results to 3D a bit later, but it's kind of easy to start in 2D. Okay, so that's our rotated coordinate system, x prime and y prime. Okay, and we know that we've rotated by an amount theta. Okay. All right. So one thing that's actually really useful in any coordinate system that you're working with is to know our coordinate unit vectors. Okay. So anytime you have a coordinate system or reference frame, you can define unit vectors that are parallel to the coordinate axis, right? So I prime here, or I prime hat, this is a unit vector pointing in the x prime direction. Okay. And then same thing for j hat prime. So j hat prime there is going to be a unit vector in the y prime direction. All right, similarly, we can make unit vectors in our original coordinate system as well. So we have an I hat, no prime, and a j hat, no prime. Okay, so I hat is a unit vector that's parallel to the x-axis. J hat is a unit vector parallel to the y-axis. Okay, now the key word here is unit vector. And so a unit vector is just a vector that has length 1. Okay, so let's use these unit vectors and let's combine it together with our orientation angle here to obtain our linear equations that we had above. Okay, okay, so I'm going to isolate the I prime vector. Okay. And I'm going to draw it a little bit bigger here just so it's a little bit easier to see. Okay, so that I prime vector there represents the same vector that we had up there. Okay, I just kind of blew it up a little bit. All right, so if we form a triangle with this, okay, where we make one edge of the triangle, horizontal, one leg of the triangle vertical, right? We can form a right triangle with this guy. Okay. Okay. Now let's use some trigonometry. So we have two sides here. So we have side A and we have side B, right? We know the length of the hypotenuse. So the length of the hypotenuse we know is the length of the unit vector, which is just 1, right? So let's use trigonometry here to obtain the lengths of side A and side B. Okay, so let's do A first, right? So relative to the angle that we're looking at here, A is the adjacent edge, right? So it's the one that's bordering that, that angle there, right? And so what do we know from trigonometry? So if we take cosine of theta, okay, cosine of theta is the ratio of the length of the adjacent edge versus the length of the hypotenuse, okay? All right, so if we have A is equal to cosine theta, we know cosine theta is the ratio of the length A and the hypotenuse, but we know the hypotenuse is length 1. And so, there's really nothing to add here. Okay. And so what we can say here is that A is equal to cosine theta. Okay. And then similarly, we can do something, the same thing for B, where B is on the opposite side of the angle theta. And so sine theta, if we do compute sine theta, sine theta is a ratio of the edge length opposite of the angle over the hypotenuse, right? So we can say B is equal to sine theta, where really that's B over 1, but we just kind of omit the 1 just because it's already applied. Okay. Okay. So what else do we know about the length A here, or the side A of this triangle? Well, we drew it so that it's perfectly horizontal, right? What else is perfectly horizontal? We know that the unit vector in our original coordinate system, xy, is also horizontal as well. So this A is parallel to x, which is also parallel to its unit vector, which is just I hat. Okay. Similarly, the B here is parallel to the original y-axis, which is also parallel to its unit vector, which is j hat. Okay. All right. And so what can we do from here, right? And so if we know that A and B are parallel to the unit vectors, we can do a little bit of vector addition. Okay. Because if we kind of pretend for a second that this A is actually a vector, and so it starts out at the origin here. Okay. And so if we go from the origin and then we go to the end of the length A, then we can say that that's a vector that points from the origin out by an amount A. Okay. And then if we go upwards from the end of A up to B, right, we can consider B to be another vector as well, right? And so if you remember your rules from vector addition, if we take two vectors and add them together, the resulting vector is going to be as if we took, the second vector and added it to the head of that vector, right? So we take this vector A, right? We add to it the vector B, right? So we add the tail of B to the head of A, right? And the ending location, that's the new vector there, right? Okay. So what we can say is that if we take the A vector plus the B vector, right? That's going to give us the vector of our hypotenuse, which is I hat prime. Okay. Right? Because whether we follow the I hat prime vector or we follow the A vector plus the B vector, we end up in the same point, which is up here. Okay. So we can say that those two are equivalent. So adding the A vector and the B vector is equivalent to just the I hat prime vector by itself. Okay. All right, so let's substitute in for the A vector and the B vector. Okay. Because we know the length of these vectors, we know that the length of the A vector is cosine, and we know its direction because the A vector is in the same, or it's parallel to I hat. Okay. Same thing for B. And so if we substitute for this, we get cosine theta times I hat plus sine theta j hat is equal to I hat prime. Question. Okay, so this equation here, even kind of very unassuming, this is kind of exactly what we need, right? Because if we look at the left-hand side of this equation, we have I hat and j hat, right? These are nothing more than just the coordinates of the vector or coordinates of a point in our original xy reference frame. Whereas on the other side, we have a vector that's in our rotated coordinate system or rotated reference frame. Okay. Okay. And so if we take this result, right, let's look back at our matrix equation that we were hoping to define through this, right? So we scroll back up here a little bit, right? If we look at the form for this first equation here, right? Well, we're saying if px prime is equal to t11 times px plus t12 times py, right? What you're going to see is that the equation that we just found is exactly the same as this, except, I kind of flipped it. Px prime is on the other side and on the right side and stuff like that, right? Because what we have here is a relationship between the x coordinate in the rotated frame and the x and y coordinates in the original frame, right? That's exactly what we have with this expression right here. Right? And so this equation here, this is actually going to form the first row of our transformation matrix equations. All right, any questions on how we got this equation here? Okay, cool. All right, so let's do the same thing. So we need to do the same thing for j hat prime. Okay. All right, so let's draw a vector in the j hat prime direction. So the j hat prime direction goes something like that. Okay. Okay. We know j hat prime is a vector, a unit vector, so we know it has length 1. Okay. And then same thing we did before. So I'm going to draw an a vector here and a b vector that connects it as well. Okay, where the a vector and the b vector here are pointing in the original coordinate system. Right? And we have this angle theta right here. Okay, so once again, let's come up with expressions for a hat and b hat that account for their the length of the vector as well as their direction. Okay, let's do a hat, the a vector first. Okay, so a vector relative to where the angle theta is positioned, that's the adjacent edge, right? So you know a vector here is going to be cosine theta. And the direction of this vector is in the positive j hat direction. So this cosine theta j hat. Right. Similarly, the b vector here, we can see that it's horizontal, but we do see that it's actually going to the left, right? So this is an important caveat too, and this is why you kind of have to be careful with the vector algebra here. So since the b vector is pointing to the left, that's actually in the negative x direction, so negative x direction from our original coordinate system. Okay? So we need to make sure we put a negative here, right? So that negative there is going to account for that direction. And now we need the length. So the length of this vector is going to be sine of theta. Right? And then it's going to be multiplied by the I hat vector. Okay. All right, so same thing we did before. So let's do j hat prime is equal to a vector plus b vector. Okay. And so j hat prime is equal to, I'm just going to swap these around just so that I vector is first. So you have minus sine theta I hat plus cosine theta j hat. Okay. All right, so let's put these together into our matrix set of equations. Okay. And so putting these together, we have, and I'm going to transform back into, instead of I hat, j hat, I'm going to do px and py. Okay. All right, so we have px prime, py prime. Okay. So remember, those are the coordinates in our transformed system. So that's in a rotated system is equal to. Our first row is going to be the first equation that we came up with. So this is cosine theta, sine theta. Okay. And this is multiplied by the coordinate vector in the original reference frame. So this is just regular px and regular py. Okay. All right, and then the second row of the matrix is going to be the equation that we have just above. So first term that we're going to have is negative sine theta, and then cosine theta. All right. So that's our transformation system, but obviously the star of the show is this matrix right here. So that matrix in that I've boxed right there, this is our transformation matrix. For a 2D coordinate rotation. All right. Any questions on that before we do a quick example of how to use this?
I have a question. Is it always going to be like this, or is this very specific to the one that we're doing?
So this is specific to just a 2D rotation here. So this is a 2D coordinate system that we're rotating counterclockwise.
Okay.
In practice, we're going to be working in 3 dimensions, and so what we're going to do later is how do we take these results or take these concepts and then apply them to 3D as well. Yeah.
Okay. And then why is only one negative sign? I would assume that we would have like one negative sign and one negative cosine.
Yeah, no, that's a great question. So yeah, so this transformation matrix is a little bit asymmetric because there's only one negative sign here. That's actually going to be the subject of our 3D transformations as well, that usually there's going to be one negative sign in the transformation. And part of that has to do with how these reference frames are defined relative to each other. Right. So remember the way that we're doing our transformations here is we're just doing a simple rotation. So we're taking one coordinate system or we're taking one XY coordinate system and just rotating it over. And so depending on the orientation of your new coordinate system, that's going to tell you where the negative needs to be, right? So I think the easiest way to kind of show this is to kind of draw out kind of both coordinate system kind of superimposed on each other. So if we draw kind of an original coordinate system like this, okay, and then to rotate it, we'd rotate upwards like this. Yeah, so the 3D we're gonna do probably in about 10 minutes. So yeah. 3D is a lot more complicated because you actually need more than one rotation in order to do a proper transformation in 3D. Yeah. Okay, so the rotation angle here is theta, and then we have this angle here, theta as well. Okay. All right, so think about transformations as kind of describing one set of coordinates or one vector in one system relative to the other, right? And so the way that we derive these equations is we look at unit vectors in the new system, and we define them basically relative to the original coordinates, x and y, right? So if you look at the x prime vector, right? And if you look at kind of where it's facing in the new orientation relative to the original x and y, right? So this x prime vector is in quadrant 1, right? So what do we know about quadrant 1 in a Cartesian coordinate system? All the values for x and y are going to be positive, right? So a point here, right? And if I describe this point here with the original coordinates, px, py, right? Since it's in quadrant 1, we know px and py are both going to be greater than 0, right? And that's true for any point here, right? So any point in this quadrant here is going to have positive x and y coordinates. And that's exactly where x prime is. And so relative to the original x and y axes, x prime is in the positive or coordinate 1. So the x and y coordinates could be positive. That's why this first row of the transformation matrix has both positive cosine and positive sine. Right? But if you look at the y prime vector, right? Because we obtained this transformation by rotating, right? That means the y prime actually has to venture into the negative x realm, right? Right? And so that's actually reflected by this negative sign right here, right? And so whenever you're doing rotations is not the only way that you can transform one coordinate system to another. You can simply also just do a simple transformation. So, or I should say translation. And so you can just move the origin from one point to the other. But when you have a rotation, one of the coordinates ends up going into the negative realm of the other one. And so that negative there is reflected within that transformation matrix. But so that's why we only have one negative, because if you look at the y coordinate of that y prime vector, it's still above 0 in that case. So the y component is positive, but the x component of that is negative, just as a consequence of rotating out that way. Yeah.
And we don't need to worry too much about like more extreme cases, at least for this class, probably because just the geometry of the human body couldn't rotate so that you end up in like the fourth quadrant or something, or like the third as much.
You could. So theoretically, this theory here, is flexible for that. So if you plug in like a very large value of theta, you'd end up, in the fourth quadrant. But actually, this would take care of that. So let's say you plug in a large value of theta of like 300 degrees, right? So that's almost a full rotation, and then you're in that kind of fourth quadrant. These sines and cosines also will be positive and negative depending on the angle that you put into it as well. So it's kind of factored directly into this matrix. Yeah. So it only looks like this just because we're only considering kind of small angles the way I draw it, but it also works for large rotations as well. Yeah. But you do bring up a good point that in reality every joint here is limited in its range of motion. So you can't rotate your elbow 300 degrees, otherwise you'd be a mutant monster. So there's ways that we can limit that later on in the theory, but this is just kind of general transformation matrices right now. Yeah. Yeah, great question. So actually that negative thing was I was planning on bringing it up later, but this is kind of a perfect time to bring it up too. So all right, any other questions before we do a quick example? Okay. All right, so let's do a quick example here about how to use these transformation matrices. Okay, so the original intention of the transformation matrix is to take the coordinates in one system and kind of see how that same point could be described in a rotated coordinate system. Okay. Okay, so let's assume a point P. Okay. Let's say that this has coordinates 3, 2 relative to the kind of traditional Cartesian XY coordinate system. I should say, not original, and traditional. Okay, so if I were to draw this, right? So we have kind of traditional X and traditional Y. And so the point P here would probably be somewhere like right here, right? For this distance here from the Y-axis to point P, this is 3. And this distance here from the point P to the X-axis is 2. Okay, so its coordinates are 3, 2. Okay, so let's say that we're going to define a new reference frame that's rotated 30 degrees counterclockwise from this Cartesian system. Okay. So I'm just going to superimpose it on the same graph right here. Right, so we have X prime, Y prime, where this angle right here we know is 30 degrees. Okay. So what we're going to do in this very quick example is we're going to compute the coordinates of P in the new rotated system. Okay. All right, so pretty straightforward problem here. So first thing we're going to do is we are going to compute the transformation matrix. So we just have a straight up rotation here, so there's not much to it. Okay, so let's compute our transformation matrix. Okay, so our transformation matrix, we're just going to plug in theta is equal to 30 degrees, and for every angle that we have there, so we have cosine 30 degrees, sine 30 degrees, minus sine of 30 degrees, and cosine of 30 degrees. Okay. All right. So hopefully everyone remembers, trig from long ago. So cosine of 30 degrees we know is √3/2. Sine of 30 degrees is 1/2. Minus sine of 30 degrees is a minus 1/2. And then cosine of 30 degrees is √3/2. Okay. Okay. Now let's take this transformation matrix and multiply it by the coordinates in the original xy. Okay, so the original xy coordinates here are just 3, 2. Okay. All right. So our coordinates in the new coordinate system, px prime, py prime is equal to, we have our transformation matrix. Our transformation matrix is √3/2, 1/2, minus 1/2, and √3/2. Okay. And then our coordinates in the original system were 3 and 2. Okay. Okay. So here is just kind of simple matrix vector multiplication. So where we can say, let me do each one individual here. So we have px prime is equal to, I'm going to take the first row in the matrix, multiply and dot product with that vector 3, 2. So we have √3/2 multiplied by 3 plus 1/2 multiplied by 2. Okay. So this is 3√3/2 plus 1. And then py prime here is going to be a minus 1/2 multiplied by 3 plus √3/2 multiplied by 2. Okay. And of course, we get a irrational number here, which we cannot simplify. So we have a minus 3/2 plus √3. Okay. And so those are our 2 coordinates for our new point. Okay. All right. Any questions on this example here? Okay, good. All right, so that's how we use transformation matrices, or at least that's kind of how they're intended to be used. Okay. What we're going to see later on, so I'll give you kind of a preview of kind of where we're going, just because I think the 3D discussion is probably going to take up the rest of the class, right? What we're going to see is that through optical motion capture, what you're actually going to be able to obtain is this transformation matrix directly, right? So through kind of the algorithms of optical motion capture, at least the way that modern software works, it's able to compute your transformation matrices straight up for you. Okay. Or for the purpose of this class, you can basically say that we're going to obtain our transformation matrices through other means. Either it's going to be given to you in the problem, or you're going to be able to compute it using some other techniques that we're going to do later. Okay, so we're very rarely going to do transformation matrices like this, where I give you the angles and you just plug in the angles and get the matrix. Okay, so you'll be able to obtain this matrix in other means. Okay. So then what's the point then? So why go through this whole theory of this? Well, if you're given this transformation matrix, so let's say that you have a new problem. So we'll say that this is kind of a whole new thing, right? And we have the transformation matrix √3/2, 1/2, minus 1/2. and root 3 over 2. Okay. So let's just say that you're given that somehow. It comes down to you from heaven. Okay. And so what we're interested in now, right? Knowing the structure or knowing how this transformation matrix was formed, right? A valid question that could be asked here is, what angle or what rotation angle was used to produce this matrix? Okay. And so that rotation angle, right? If you're given this transformation matrix through a motion capture system, that rotation angle is going to be the joint angle that we're looking for in human motion kinematics. Okay. So this is how we typically use it. So typically, we're going to compute the transformation matrices in some other way, and then we use the numerical values in that matrix to compute the joint angles. Okay. So for instance, one way that you can do this, and so, you don't need to use every entry here in the transformation matrix, right? So let's say we take that entry right there, right? And so what we can say is that sine of theta, where theta is unknown at this point, is equal to 1/2, right? And so what we can say is that theta is equal to sine inverse of 1/2, okay? And then that's kind of what we obtain, or that's what we compute when we're doing human motion kinematics, okay? So this is how a transformation matrix can be used to find rotation angles. Okay. So I wanted to mention that just because, I have this point later on in the notes, but I don't know if we're going to get there today, just because there's a lot to talk about with 3D transformation. But, I want to make sure that, everyone kind of has an idea of where we're going, because compared to where we ended the class on Monday, this has been kind of a very large detour. And so whenever you take a large detour, it's always good to remember kind of where you're going, just so you kind of remember kind of why we're doing this all in the first place. Okay. All right, any questions on this? Okay. All right, so let's talk about 3D transformations, or I should say 3D rotations, or I say 3D transformation matrices. We'll go with that. Okay. So going from 2D to 3D here is actually a very big jump, because all of a sudden in 3D, we have a lot more rotational degrees of freedom, okay? So 2D, angular kinematics is actually very easy in 2D just because, we only have one rotational degree of freedom. So when you're two dimensions, there's only one plane that you can rotate in, and there's only one angle theta, right? In 3D, okay, in 3D, we actually have three rotational degrees of freedom. Okay. So this is up from 1 in 2D. Okay. And so if I draw kind of a generic 3D coordinate system here, right? So we have X, Y, and Z. So we can actually rotate in all three of these coordinate axes, right? So if we do a rotation in X, we can do a rotation in Y, and a rotation in Z. And all of those are valid rotations, right? So think of a Rubik's Cube, right? So if you've ever done a Rubik's Cube, you can do rotations in all three, planes right there, okay? So what this also means is that we have three different, ways or three different angles that we have to account for when we're doing rotations in 3D, okay? And so our transformation matrix has to also reflect that as well. Okay. So this is a lot more complicated. And so, and it's a lot harder to visualize than just than the 2D one as well. Okay. And so, I think the best way to do this, or kind of the way that kind of makes the most sense to me, is that to obtain the 3D transformation matrix, you can think of it as a series of 2D transformations, applied one after another. Okay. Okay. And this works too, considering the mathematics of transformations as well. So if you think back to the last example that we did, right? To obtain the coordinates in the new system, all we did was we multiplied our transformation matrix by a vector, right? So think about, if we had a third coordinate system. So let's say that we rotated even further. And so if we wanted to kind of get the coordinates in that third system, we just have to take our results from before and multiply by another transformation matrix, right? So kind of the upside to that is that, these transformations you can apply sequentially one after the other. All you have to do is you just have to keep multiplying the matrices one after another, right? And that's kind of the beauty of kind of this transformation vector algebra framework here, is that it all relies on just linear algebra. So you can just apply multiple transformations one after another by just keep multiplying these matrices. Okay. So if we apply that logic here, if we come up with 3 separate 2D transformations and just multiply them all together, that's going to give us our 3D transformation matrix. Okay. All right, so to help visualize this, I actually have an analogy for you. Okay. So let's imagine that you're in an airplane and the airplane is about to take off. Okay. So the transformations that we're going to apply are going to be all the same kind of maneuvers that an airplane does as it takes off. Okay. All right. So I'm going to draw my best. I'm doing my best to draw an airplane here. Believe it or not, the airplane in my notes actually looks really good. But then every time I draw this in the lecture, I get nervous and I draw an ugly airplane. But here we go. Okay. Okay, so those are the wings. This is the body of the airplane. And this is the tail. Okay. I got nervous again. Stop, it's not, it's okay, it's okay. All right. All right, so let me go ahead and draw our coordinate system here. Okay, so imagine the plane is sitting on the ground, right? So let's align our original Cartesian coordinate system, X, Y, and Z, with the orientation of the plane. Okay? So let's say that the original X coordinate is down the axial length of the plane. Okay? We're going to say the Y direction is going to be along the wings. And then the Z direction is going to be pointed downwards. Okay. All right, so our original okay. And so as this plane takes off, or we're actually going to describe it on the runway as well. So as the plane goes along the runway and takes off, you know, this plane is going to perform maneuvers along by doing rotations along each of these three axes. Okay. And so we need three different angles to describe this. And so let's say that we have an angle rotation about the z-axis here. So that's going to be our angle theta. Okay. Next, we're going to have a rotation about the y-axis. And so that's going to be the angle phi. And then a rotation around the x-axis here, that's going to be the last one that we do, is going to be the angle psi. Okay. Okay, so theta is rotation about the z-axis. Okay. Phi here is going to be a rotation about the y-axis. And psi here is going to be a rotation about the x-axis. Okay. So our final transformation matrix is going to have all three of these angles here. Okay. But again, we're going to apply these transformations one by one, and then multiply their transformation matrices together to get our final transformation matrix. Okay. Any questions on just this analogy here? Okay. All right, so let's go ahead and start transforming. Okay, so you know, when your plane is sitting on the runway, right? And so, you know, one thing that it usually does before it takes off is that it usually is taxiing along the, you know, along the airstrip, right? So step one, taxi. Okay. So during the taxi phase, you know, the airplane is basically like a car, and so it's kind of constrained to be kind of, you know, parallel to the ground, but it may have to turn, right? So as the airplane's kind of driving along, you know, the airstrip, you know, it may have to turn to orient itself with the runway. Okay. And so think about how your car turns, right? So when your car turns, right, you're basically doing a rotation in one plane right there, right? And the axis that you're rotating around is the z-axis. Okay. So let's write a transformation matrix, a 2D transformation matrix that describes this rotation about the z-axis. Okay. All right. And so let me go ahead and do this. And so let's say that we have let me define it this way, actually. So let me say that this is px, py, pz. Okay. So these are coordinates in our original frame. Okay. And so this would be px1, py1, pz1. Okay. Actually, let me label the ones on the left with a 0, because that's kind of our starting point. Okay. So these are the coordinates. In our original frame. And these are our coordinates after step one. So after we just do a rotation about the z-axis, this is our coordinates after one rotation. Okay. All right, so this is just simply a 2D transformation, right? So we're just rotating about one axis, so we can apply our 2D transformation matrix here, okay? But you might be thinking, you know, wait a minute. So this is a 3D situation, and our transformation matrix that we went over before was only 2D, all right? So when you're doing just a 2D transformation in 3D, you know, there's one coordinate direction that's going to be locked, right? So it's basically going to be the same as before. And since we're rotating about the z-axis here, right? Performing a rotation about the z-axis is not going to change your z coordinate, right? And so you're only going to be changing your x and y. And so the z coordinate here is actually going to be fixed. And so one way that we can do that is we can just make sure that our last row in the matrix is just 0, 0, 1, okay? And then we also need to make sure that everything in that column is 0 as well, okay? So by making the last row in the matrix 0, 0, 1, you know, we are, you know, ensuring our z coordinate doesn't change as a result of this rotation, which makes sense, you know, because we're rotating about the z axis. Okay. Yeah.
Should it be reversed to the coordinates after the first rotation, which you have not?
Yeah, so we're doing it this way just because of traditionally how the 3D transformation is defined, but it is actually going to make a difference in terms of how we define the angles here.
Okay.
So if you remember in the 2D transformation matrix, you know, we had that negative in the bottom left corner, right? And that's because that transformation was from the original coordinate system to the new one. This one, we're doing it reverse. And so that's actually going to swap the location of the minus sign. And so here, we're going to have cosine theta, right? Because we're doing this rotation in kind of the opposite direction, the minus sign term is going to be up here, okay? And then we have a sine theta and then cosine theta, okay? So since rotation order is different than before, it'll become clear why we do this a bit later, but you know, just kind of bear with me for a second, okay? Okay, but just kind of make note of that. So, you know, usually in our other ones, the negative sine theta is in the bottom left, but because we're doing the rotations in the opposite order, you know, that sine theta is up in the top. Okay. Okay. So that's step one, right? So step one is just taxiing on the ground. And this rotation matrix accounts for the fact that, you know, we may turn the nose of the airplane either to the left or the right, depending on, you know, how we're getting on the runway. Okay. Okay. Step two. Oh, by the way, if you want just a little bit of trivia, you know, the rotation that we just did in kind of aerospace terms is we just performed a rotation in the yaw, right? So we just did a yaw rotation. Right? It has nothing to do with biomechanics, but you know, in case you're curious about, you know, aeronautical terms. Okay. Okay. Step two. Step two, we're going to take off. Okay. And so for takeoff, you know, usually your airplane is kind of speeding down the runway and is trying to gather enough speed for it to generate enough lift for the nose to come up, right? So in takeoff, the primary maneuver or the primary change in orientation that we're going to do is we're going to point the nose upwards. Okay. And so in terms of our original coordinate system, this is going to be rotation about the original y-axis. Okay. And if you want kind of the aeronautical term for this, this is pitch. Okay. All right. So I'm going to go a little bit quickly here just because, you know, I want to make sure to get to the final transformation matrix before we end today. So for the pitch rotation, this rotation here is going to be a bit more traditional in the sense that, you know, the sine term is going to be back in the lower left. but this is mostly just because of how we oriented the y-axis as well. Okay. Okay. So the rotation matrix here. So let me just go. This is going to be px1, py1, pz1. Okay. This is equal to. And remember, the y-axis is the one that's fixed now, and so we need to move the location of the ones and the zeros. Okay. And also, our angle is different here as well. So we need to make sure, don't use theta again, because we've already used theta for the z rotation. Okay. Okay, so the angle that we're using here is phi. So we have cosine phi, 0, sine phi. Our second row, that's going to be our fixed line there. So we have 0, 1, 0. And then our last row here is minus sine phi, 0, and then cosine phi. All right, and this is be px2, py2, pz2. Okay. Okay. So again, the location of the sign is there is in the bottom left again, just because of the way the y-axis is oriented and the way that we're rotating about that axis there. Okay. Okay. So our last rotation here is going to be a rotation about the x-axis. Okay. So this is, now that the airplane's in the air, we need to turn in the air usually to get on our desired flight path. Okay. So in this case, we're going to rotate. So we're going to point one of the wings downwards and the other upwards. Okay. So this is going to be a rotation about the x-axis. Okay. And then the aeronautical term for this is roll. Okay. So you're basically, it looks like you're basically rolling the aircraft. Okay. Okay. And so the transformation matrix for this, so we're going from configuration 2 to configuration 3. Okay. So we have px2, py2, pz2 is equal to. Okay. Now our x coordinate is the one that's fixed. So we have 1, 0, 0, 0, 0, cosine of psi minus sine of psi, sine of psi, cosine of psi. Okay, and we have px3, py3, pz3. Okay, good. All right, so we have our 3 transformation matrices here, okay? What we desire in the end is we desire a transformation matrix that takes us from our original configuration to our final one. So after we performed a rotation in X, Y, and Z. Okay. And so the way that we're going to combine them together is we're just going to multiply them all together. Okay. Okay. So I'm going to give our transformation matrix a symbol here. So usually we use the symbol R to denote a transformation matrix. Okay. And our combined transformation matrix, right? The notation that I use here is I use the superscript to denote kind of the ending configuration. And then the subscript there is to denote the starting configuration, okay? So the way to interpret this transformation matrix is that this transforms coordinates in configuration 3 into coordinates in configuration 0. Okay. Which seems reverse, right? So, the way that we kind of describe this example, we're going actually from 0 to 3, but it turns out these transformation matrices are also reversible as well. And so if you want to get the transformation matrix in the opposite direction, okay, so let's say you want to get 3R0, so that's the transformation matrix from configuration 0 to configuration 3. All you have to do is take the transpose of the other one. Okay? Okay. And so it doesn't really matter which direction your transformation matrix is defined in. You just have to take the transpose to get the other direction. Okay. All right, so let me give you the final result here, just so I can kind of leave you with that, and then we'll pick this up on Monday. Okay, so multiplying these three matrices together, we get quite a doozy. So we get cosine phi, cosine theta. Okay. We get sine of psi, sine of phi, cosine theta, minus cosine psi, sine theta. That's just the second column entry. Right. And we have cosine psi, sine phi, cosine theta, plus sine psi, sine theta. Okay, that's just the first row. Okay, second row. Second row is basically almost the same as the first row. Second row, we have cosine phi, sine theta. That's the first column. Second column, we have sine psi, sine phi, sine theta, plus cosine psi, cosine theta. Then we have cosine psi, sine phi, sine theta, minus sine psi, cosine theta. Okay. Don't worry, we're hardly going to use the first two rows, and so don't panic too much. Okay, because the last row is the one that we actually use the most, because this is the easiest one to compute angles from, which remember, that's kind of what we're interested in. Okay, so the last row in the matrix, we have a minus sine phi, sine psi, cosine phi, and then cosine theta, cosine phi. Okay. All right. So again, most of the time we're going to use the last row because remember what we're interested in is computing angles. And so the easiest way to do that is from the last row in this matrix. Okay. All right. Any final questions on this? Okay, so I apologize. I know I went over time a little bit. I'll leave this up here for the next few minutes for those of you still copying it down. But just know that this matrix is in the notes as well. Okay, so when we come back on Monday, remember, first thing on Monday, we're going to go over the final project. And so we'll talk about these, the instructions and the requirements. One thing you guys should be thinking about is, forming your groups. And so if you can form a group of 4, that would be perfect. Okay. Just so that you can kind of get started on the final project after we talk about it on Monday. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you on Monday.
Oh, okay. I can do it, but I think you'll do it, yeah, I have, put that, I think, yeah, this is gonna be that. Because we really how. That's cool, man. Yeah, I would say try. You got anything for it? No, man. There you go.
See you guys. Have a good weekend.
Where's the aero polo, man? We talking about aero today.
Oh, we are? Oh, I'll bring it tomorrow.